Today I was testing some semiconductor detectors from Swiss company Teviso. They are pin diode detectors, and the detector itself is just beneath this little window here. You can see this whole integrated circuit. And the product specifications say that this type of detector, the 2014 solid-state radiation sensor, is good for detecting beta and gamma radiation as well as X-rays, but it also says that output pulse width 40 to 150 microseconds depending on pulse energy level. So I was curious if it's possible to perform gamma spectroscopy of sorts with these detectors, even if it's just at a low resolution. I also have another type of these detectors. This one here that doesn't have a real labeling is actually the model 2007, which is supposed to be detecting low energy X-rays, beta and gamma radiation. So I have this little nifty circuit board. Let's insert one of these detectors. Connect the power supply. And then you can see we have a little matrix here that is supposed to tell apart those different pulse widths. So let's see. Here's the detector and my cesium 137 check source, which is 662 keV gamma radiation. Let's place it at the detector window. And you can see it takes a while to refresh, but you can see we're getting the majority of pulses in the higher energy area over there on the right, which kind of makes sense because these channels here are not calibrated to a certain energy yet. It just means that on the right it's more energy, on the left it's less energy, but it's not calibrated to a specific range yet. So if we reset the device, after resetting the device, we're going to use a barium 133 calibration source, which has lower energy gamma radiation, something around 300 kV. There's much more than just one gamma line in it, but it should be much less energetic than cesium 137. So let's place that under the detector as usual. It still gives a much lower reading. That's because it's only gamma radiation. While the cesium 137 also has beta radiation, which is also detected by this little chip here. So that's a little flawed in that case. But you can see we have more impulses in the lower bins right here, and there's not really anything in the rightmost bin or in the rightmost bins, where there was a lot with the cesium 137. I'll do that again. Cesium 137. As I said, we have to wait a little for it to refresh. Now you can see we're getting more in the high energy area right now. But we're still not getting anything in the lower bins right here. So what's best to do is to use X radiation, because X radiation has a broad spectrum of pretty much any energy. Let's have a look at the X-ray spectrum before we start. Okay, so let's have a look at photon spectra. This will be the energy and the amount. For now it doesn't matter too much, you know, with 662 keV that we had from cesium 137, it only has one single gamma radiation line, pretty much. And the barium has quite a few different lines, somewhere in the area, something around 300 kV. I don't know offhand right now, and there are multiple lines, but you can see the average photon energy would be much less than that of the cesium 137. Now with X-rays, you also have characteristic X-ray radiation, which I'm not going to explain too much about now, because then the video would be too long. Maybe I'll do that in another video. But you can pretty much discard this characteristic X-ray radiation. The most stuff that occurs in the conventional tube and a conventional tungsten anode tube, which I'm going to use, is Bremsstrahlung, which is a continuous spectrum that runs in a linear fashion with most of the photons being emitted in the lower energy range and least of them in the higher energy range, with the maximum photon energy being your anode voltage pretty much. So it could be 40 kV if you set the anode voltage to 40 kV, 60 kV, 100 kV, whatever you set the tube to. But this linear fashion photon energy flux pretty much is just a theoretical spectrum, because there's actually filtering or shielding happening within the tube material itself. You know, the X-ray tube is made out of glass. It's a vacuum, but of course it contains something around it, and that is glass typically. The window is made of glass in our tubes. The anode material itself shields some X-rays, so you pretty much filter out most of these very low energy X-rays. So your real spectrum actually looks like this, pretty much. So you have very few, or pretty much it starts here actually. So let's draw it again. kV, I'll just say we have about 80 kV here. Then your real spectrum looks pretty much like this. So you have a lot of photons in the medium energy range, maybe something like 40 kV. There's 80 kV photons as the maximum energy, and there's pretty much nothing at 0.01 to say 10 kV or something like that. So that's what your spectrum actually looks like, with the maximum energy, as I said, depending on your set anode voltage. So this is important to remember. In X-rays, you have a spectrum of all kinds of energies that are distributed over a very broad area. Anything from 10 to 80 kV will occur in the spectrum. Well, if you remember the cesium again, it's just a single line at 662 kV. So when checking X-rays with this device, you know, we should have a broad range of energy pulses, even in the lower energy area here. Maybe not the first bins, but anything above that. Because as I said, the bins are not exactly assigned to a specific energy as of yet, but we should have a spectrum distributed over the entire area, pretty much. So let's check that out. RD 2014, 40 kV, 25 milliamps, 500 milliseconds. So this was my first test run, with just a very small radiation field of about 2 by 3 centimeters, just pretty much covering the detector, not exposing the camera to much radiation. Okay. 60 kV, 25 milliamps, 500 milliseconds. But well, this stuff didn't give me a lot of pulses. Most X-rays went through unnoticed, even more so with the higher energy X-rays. So I actually swapped to a much larger field, about 20 by 15 centimeters, covering the entire detector, and seeing if I get more pulses. So same parameters, the anode focus to detector distance always being 90 centimeters by the way. 40 kV, 25 milliamps, 500 milliseconds. The only thing, as I said, that I changed was using a much larger radiation field, so I have stray radiation as well. Resetting detector. $60 kV, 25 milliamps, 500 milliseconds. You can see that the stray radiation as seen by the camera has drastically increased with increasing photon energy. Okay. You can see the distribution of impulses in the bins is rather odd and not as expected actually. 80 kV, 25 milliamps, 500 milliseconds. Resetting device. Continuing with 80 kV. So now the camera is actually seeing a lot of stray photons, or stray electrons. 100 kV, 25 milliamps, 500 milliseconds. And as the spectrum shifts more towards the high energy range, the detector begins to see less and less. Less than I actually expected because, as I said, in the distribution there's still all those lower energy X-rays. Test complete for detector RD2014 swapping detector. Testing detector RD2007. Background radiation. Forming test with 100 kV, 25 milliamps, 500 milliseconds. Remember, this is the detector which is supposed to be better at detecting low energy X-rays. Quite interesting impulse distribution there. Resetting device. Forming test with 80 kV, 25 milliamps, 500 milliseconds. Pretty much didn't see anything there. Well, you could see that the camera saw the X-rays, so there was radiation there. Forming test with 60 kV, 25 milliamps, 500 milliseconds. Well, maybe it saw a few impulses, but the background is quite high on this detector. Resetting device. Forming test with 40 kV, 25 milliamps, 500 milliseconds. As of our expectations, this should be better now, so let's see. Yes, indeed. That detector seems to be only good at detecting lower energies. Again, weird distribution. Test complete. With detector 2007. Now if you take a look at these readings on semi-logarithmic paper, you can see that both of the detectors, both the RD2007 as well as the RD2014, seem to work best or detect most of the photons in the low energy range, which is expected as most interactions happen as the photons have lower energy. Then there's a drastic decrease at detection at 60 kV, which you can see here, with the RD2007 scoring remarkably worse than the 2014, which you can hear 60 and 60 kV here. And now we have the next 80 kV and 100 kV, where the behavior is actually very similar. You can see that at 80 kV, both detectors are worse than at 100 kV. This is probably due to Compton scattering, because as I said, I used a large field to measure both these detectors, and at 100 kV probably Compton scattering, and thus lower energy photon and pretty much beta radiation or electrons were detected to a greater extent than at lower energies. This would explain it in theory, but I didn't have time to conduct more of these tests, so probably I'm going to redo that again at some other time and measure with more different energies like 40 kV, 45, 50 and so on, and not just in steps of 20 kV. So this would be the comparison reading with an energy compensated ion chamber. You actually expect pretty much an exponential function, not quite, but pretty much an exponential function. So on semi-log paper this would be almost linear. You can see an increase of the actual dose rate, as I said, in energy compensated ion chambers, so they have the same detection probability for higher energy photons as well as for lower energy photons. These detectors never claim to have that, so it's just a rough comparison just so you get an idea of a different detector system. But yeah, I think these little things are rather promising because they're like, think about 80 euros a piece, and if you can do the circuit yourself, it should be pretty simple to get a nice detector. And it's not too good at background radiation, because background radiation just produces a few impulses every minute if at all. And electromagnetic fields are also an issue, so if I run it in this room, For example, my mobile phone is near them, and that's a problem. That's probably because of the circuitry that isn't properly shielded, though. It's not those detectors. So, but yeah, it's just quite interesting. This little pin diode detector is quite interesting. So, well, I'll do more experiments on that in the future, I guess, and I'll keep you updated. Thanks for watching.